Okay, now let's look at the other term of assumption, which is that the environment was assumed to be fully observable. So let's see what if this doesn't hold good. There are two things to observe for this specific problem we're discussing, one of them being the location and the other one being the map. We'll briefly look into each one of them. So let's start off with the location. So now I say that my location is not observable. I do not know where am I, nor will I know where am I till the entire time my agent is moving around the system. So let's take in a very small map like this. It's the obstacle, of course, and this is my happy goal. And all I need to do is reach the goal, but I do not know where am I. Is it really possible to solve this problem? Every search started out from the source. You don't even know the source. So let me mention in the sequence, I do not know whether the sequence will solve the problem that we are trying to solve, but then let's try to find out. So it's up, up, right, right, up, up, down. So I don't know where my source is. What if I am here? So let's apply up, up, right, right, up. Now from here, if I turn up, of course I hit myself. However, I cannot break the constraints of the problem. I'm not a ghost that will go outside the world. I cannot travel walls. So from here, if I apply up, I'll still be here. Similarly, from here, if I apply right, I cannot go beyond walls. So I'll still be here. So let's say up, up, right, right, up, I'm here, down. Wonderful, I reached the goal. It's not the best way out, but I still reached the goal here. Up, up, okay, I hit myself, but I'm still here. So up, up, right, right, up, I hurt myself, down, I still reach. Up, right, right, up, down, I still reach the goal. Up, right, right, up, down, I still reach the goal. Up, right, right, up, down, I still reach the goal. Up, right, right, up, down, I still reach the goal. Up, right, right, up, down, I still reach the goal. Up, right, right, up, down, I still reach the goal. So bad assumption, I don't even know my source, but it turns out the sequence is actually doing okay. It could make me reach the goal. Many times I actually went to the goal, missed it, and came back again, which may sound weird, but I always reach the goal. Now let's see, how do we solve this thing as a problem? And in order to solve the problem, I'll coin a new term called as a belief. So state is the exact encoding, the exact position, the exact knowledge about yourself. That is what is called as a state. In this problem, I don't really know the state. A belief is a collection of states where you believe you might be there. So a belief is a collection of states where agent is likely to be in, or a belief is a collection of all states where the agent is likely to be in. And therefore, for this problem, can I write down what my belief is? Now, I'll still draw it as a circle. Sometimes I like to draw it as a cloud just to say what is inside that is my belief. So my belief is I am either at 1 1 or 2 1 or 3 1 or 1 2 or 1 3 and so on and so forth. I'll not write down all of them. This is what is called as my initial belief. And I'll model the problem as a search problem in this space, which instead of a state space search that happens on states will be called by a similar name, a belief space search on a belief spaces. A state space was a collection of all the states. A belief space is a collection of all possible beliefs. So over here, if you need to find out what is a belief space, every state or a belief space size, the state space is 1, 2, 3, 4, 5, 6, 7, 8. 8 states is the state space. Belief, any one of these terms may or may not be there. So it's 2 raised to power state space size, or it is 2 raised to power 8 is the belief space size. So the belief space is always exponential to the state space size, also called as doubly exponential, because the state space is said to be exponential on the state representation encoding parameters or the state variables. So state space is exponential to the state variables, belief space is exponential to the state space, so belief space is said to be doubly exponential. That's a homogeneous space that we're talking about. Now, I leave it for you with search algorithm, BFS, DFS, uniform cost search, whatever, but all of them will have some kind of the actions possible, and action A is considered in this space if and only if it can be applied on at least one item of the belief space, and mostly you'll get up, down, right, left. At least one of them, up, down, right, left, will be feasible. So instead of feasible actions over a state S, we talk about a feasible action on any one of these states. So my loop, which was for all feasible actions A, turns out to be for all actions A that are feasible on at least one item of the belief state. All my total number of actions which are possible over here comes out to be a union of all the feasible actions for all the states. So the actions that I will be considering as my action set will be the union of all actions such that A is in a feasible actions for the state S, where S is in my belief state B. So that's my belief state. And these are all the S's. And now I need to apply the action. So for this particular problem, let me just take an example of one action top, and I'll only draw it for one action top. Now if I'm at 1 1 and I take a top, I get to 1 2. If I'm at 1 2 and I take a top, I get to 1 3. If I'm at 1 3, I take a top, I remain at 1 3. It's a set. Duplicates don't matter. Similarly, if I'm at 2 1, I take a up, I remain at 2 1. I cannot be on the obstacle. If I am instead at 2 3, I take a top, I remain at 2 3. If I'm at 3 1, I take a top, I go to 3 2. If I'm at tree 2, I take a top, I go to tree 3. If I'm at tree 3, I take a top, I remain at tree 3. Now, this specific example, the beliefs reduce with time. The number of states variables in my belief space, they become lesser. Of course, I started off with the maximum possible belief state. No matter what you do, it will either be unchanged or nothing will happen. So earlier we said s dash is equal to a of s. Now we will change that from a state space to a belief space. I say b dash is equal to a union of the action A applied on all the states S, where of course S is the belief state B. And it's a set, so I just take on a union. If they are duplicates, they do not come. And this was the S dash, and you're basically taking a union of all the S dash. So that is what is my actions. The other point being, states are okay, actions are okay, so my graph is modeled, so I can somehow do a graph search, whatever you have. What is the goal state? The goal state is, for this particular problem, that my belief state has nothing but the only goal, which is tree 2. In general, the goal test passes the belief state B if and only if the goal test passes all S for all S in my belief state B. So when all the states in my belief state pass the goal test, I say that goal test is what is a passed goal test. Now, unfortunately, I did not say what about the cost, because the cost is CSA S dash. It depends upon S, it depends upon S dash. I only have A, and therefore I can, for this problem it's simple. CSA S dash is equal to 1 for all SA S dash, so you could just add up 1. In general, it will be a little bit more difficult. The way that we do that is by redefining the belief, and the belief is redefined not only as a collection of states. So it's not only a collection of state, but it's also the probability that you are at a state S. So initially the probability of everything is 1 by 8. We'll deal with probability towards the closing of the lecture again. Here I have simplified it up. There is no probability. So all you could do is that probably calculate the states cost for all combinations and use that as an indicative cost. Now, just to tell you how probability really works, the one tree that you saw over here, which is this one tree, there are two ways of getting it. You were at one tree with a probability 1 by 8, and you did nothing. You went up but came up over here. The other, you were at 1 2 and you came up, so it should indicatively become 1 by 8 because of this, and another 1 by 8 because of this, 1 by 4. But of course that's speaking out a little bit informally. So this is what is called as a belief state search without any kind of knowledge of where you are. And if you need to apply A star algorithm heuristics, there are two distinct things that you do. You end up taking heuristics which are good for all the items in your belief state, if you can calculate the probability for probabilistically for all the items in the belief state. And the second is more of exploration. If something gives you a better indicative idea of where you are, then also it's a very good heuristic. So in robotics, it's a famous thing. Many times a robot may have to walk back when the goal is definitely in front, because going back, it gets to know where it is. If you are driving without Google Map, remember last time you actually had to hit the reverse gear because there was a famous intersection and you had to take the fifth right after that intersection. Going back reassures you that yes, your location is now known. Then you start counting 1, 2, 3, 4, 5, which otherwise you completely forgot, or there was a vehicle and you missed one, felt fishy later upon. So that's what happens. Now, sometimes it's simple. Sometimes you have the problem which is called as you need to search in a belief space. However, you are gifted with a sensor which leads to observation. So let's take in exactly the same example and say that for this specific grid, all that you have is a special kind of a sensor, and that special kind of a sensor gives you an accurate distance from the right wall, and the distance from the right wall turns out to be 1 unit. So automatically your belief space is either this or this, as the others, if it had been this, distance from the right wall was 1 and 1, 2. Okay, this is also valid because distance from the right wall is 1, distance from the right wall is 1, distance from the right wall is 1, distance from the right wall is 2, distance from the right wall is 2. So if I observe a distance from the right wall as 2, then it's either this distance from right wall 2 or this distance from right wall 2. So how do we really model this in our belief space? Now, believe me that this is a sensor, and the sensor will have to be invoked. The readings are not going to come flying. There's a sensor, you have to hit that sensor, call the calling program, and that will come back in. So again, the only thing that sensor does is that in my search, in my belief space search, there is one action which is the sensor readings, which is controlled by God. I'm not controlling it. The distance from right wall may be 1, maybe 2, maybe 3. I don't know. Only God knows. So, in such a case, what happens is that I'm dealing with a kind of problem wherein I am again doing something similar to an ant or graph search. So I've got my own nodes that I do it on a belief. So now it's not the same old circle, it's a belief, and hence the cloud. If I decide to invoke a sensor, the sensor gives me values. Now again, for actions, I said, and you'd consider an action here as long as one of the states in your belief has it, it's feasible on that state. Similarly, you select one of the sensor readings 0, 1, 2, 3 as long as one of the states has it. However, immediately after you get a value, you may be able to reduce your belief space size. So let's go on the same problem, all states possible. So from 1, 1 to 3, 3. However, after that, I did invoke the right sensor, and my right sensor says the distance from the right wall is so distance from right wall is equal to 2. Now I go on to this state and I put a cut on the values which do not have distance from the right wall as 2 or do not adhere to the sensor readings, and the only states where distance from the right wall is equal to 2 are 1, 1, 1, 2, and 1, 3. All the others do not have distance from the right wall as 2. So using sensors, I can immediately compress it up. The only thing is that the sensor actions may also have cost. So the cost of this over here is the cost of all the actions taken plus the cost of invoking in the sensor. Sometimes sensor use is free, so just use as you like. Now, sometimes what happens is that I'll have a belief space, I'll have a sensor observation, plus I will have stochastic actions. And I'll not repeat it up. You could do both the things simultaneously over here. So just to give you a brief indicative idea about how the tree would look like, you can visualize it for yourself. So you got your initial belief state, you take in multiple actions, and let's say the action was 1, 1, and one of the actions, this is all node that's being controlled by me, the action is right. Now from 1, 1, if I take the action right, I either go to 2, 1, or I go to 1, 2, or I stay at 1, 1. I either go here, or remain here. There are 3 actions possible. So now what I'll say is the starting of my belief is 1, 1, 2, 1, 1, 2, and similarly I'll do the same for everything else. So instead of contracting, mostly it would be expanding. However, I did not show the God node, by the way. I should have shown the God node as well. Now I can invoke in my chance node, which is my sensor, and I can make use of this sensor value and tune it up further. So sensors reduce in reduction in the belief, and the stochastic action increase my belief, and that's how intuitively my search would really go upon. Now, there is, of course, a name when you do it up, and they always come in this action. You move, and then you apply the sensor. Then you move, you apply the sensor. This is called as the prediction step, and this is called as the update step. Not really important. Now, problem with belief spaces, state space searches are already too large, too humongous. Belief space is exponential to state space. So it turns out that I'm also telling you about realism. I'm also telling you about what is practicality. And practicality, if you really believe that this will work, then obviously not. So again, there are some options which you have. I'll go with the classiest one. Now, not knowing anything is one extreme case. Normally you have at least some idea. So you split the problem into 2 parts. One is you heuristically select one action. So you look at all the values and you say, by heuristic, let's apply that action. It's so computationally efficient, I'm not getting an optimal solution. Assume there are no dead ends. Then what you do is you apply that one action. Then you update your belief. And using the new belief, you apply a new action. Some actions take you closer to the goal from the given belief. Some action reduce your belief. So you were driving, you lost a count of seventh right. So what do? Some actions, they say that, okay, keep going right. We've got more sensors, we've got more indicative measures, we'll still be able to make it. Some say, okay, go back because your belief would suddenly increase. So some action take you closer to the goal, some actions take you in consolidating your belief into the exact location value that you can derive. There are special names for it, like this is also called as a localization or a filtering problem. And this is what is called as the active planning or the active localization problem, where the term active says that you are somehow intelligently picking up and placing in one action which is possible. The other thing that you could do, of course, is again interleaving. So you do some belief space, then you do take an action or a sequence of action. Your update becomes belief. From that as a source, you apply a new belief state. So instead of heuristically selecting one action, you could do a limited search just like the previous time. Sometimes you again say that, okay, if something has a very low probability, let me discard that up. So you go with optimistic belief knowledge. So yes, there may be things which are not in the beliefs, which are in the belief state, but you say that, okay, I take those kind of chances and I go. If it doesn't happen, then I locally repair, globally repair, and I will do in all those sorts of things. So I mean, that's practically what we are using, not going by full-fledged, high-end, complicated searches.